the covariant derivative, the need for a new object is obvious. It's the fact that the partial derivative of a tensor is not a tensor. Because when you study the rule by which it transforms from one coordinate system to another, you discover there is a part that does transform according to the tensor rule, and then there is another part that breaks the tensor rule. So it doesn't even matter what this is, but the fact that there is an additional term means that this is not a tensor, and therefore we have lost our recipe for constructing invariant objects. So we need a new operator that fixes this, something that would have all of the nice properties and insights of the partial derivative, but will have the additional property that it produces a tensor output for a tensor input. So that's our goal. And then there is another thing that's not particularly nice about the partial derivative, and it's the fact that when we're studying vectors, especially now in the age of computers, we really want to deal with the components of the vectors. And taking derivatives of the components of the vectors with respect to coordinates, stick to numbers. And it turns out that because the associated basis changes from one point to another, that finding partial derivatives of components of vector fields is not sufficient for understanding the rate of change of the vector field, because you also need to know the properties of the basis changing alongside. So that's another disadvantage, that you sort of have to keep track of how the base is changing as you're studying the rate of change in the components. So let's see it. There's just one calculation that shows this problem and almost suggests a solution. So let's consider a vector field V, which depends on coordinates. Variable vector field V, doesn't matter where it came from. It could be the gradient of something, or it could be just a velocity field. And we want to study how this field changes from point to point. So let's actually take the derivative with respect to zk. And let's go straight to, so point number one, this is a vector. Do you guys agree with me? We know that derivatives of invariants, partial derivatives of invariants are tensors. It was the first tensor that we ever considered. And because this is an invariant, and we're just taking its partial derivative, this is a tensor of order 1 with vector elements. And we're going to do it this way. We're after the components. So we will represent the vector field as VI Zi, its representation with respect to the basis. And we see right away why the variability of the covariant basis matters. Because when we're about to apply the product rule, we'll get dvi dzk, which is the sort of thing we want, 9 numbers. That's our studying the rate of change of the components of the vector field. That's what we would like to concentrate on. But then there will be a second term, which is dzi dzk, which is the rate of change of the basis. And that's the other half of the information. So if we just stuck to only looking at dvi dzk, we're missing half the information in order to evaluate this derivative. All right, so let's see what we get. We get dvi dzk zi plus vi, the derivative of this, plus vi dci dzk. Okay. And we know what this object is. Well, not know what this object is. We know how to represent this in terms of the Christoffel symbol. The Christoffel symbol was invented for this. And let me just point out 2 things. This is not a tensor. That's how we started this segment. This is not a tensor. Similarly, this is not a tensor. But the sum still is a tensor because, there we go, it still is a tensor. So we're still holding on to meaningfulness here. It's just that it's broken up between 2 not fully meaningful objects. So this term will leave as it is, dvi dzk zi. And this object we'll write in terms of the Christoffel symbol, plus vi. So this is gamma lower ik, upper j. So gamma j I k z j. I'll pause for a moment for all the puzzle books to go away. You guys are with me? So here's actually a demonstration of why this is such a natural object. It arises naturally in the course of analyzing, asking a very obvious question. So now the next step I will actually do in place. What I want to do is factor out zi. 1 second. I'll answer in a moment. Zi. So I want this to be zi. So I will actually rename j into I and I into j. That's just the renaming of dummy indices. Everybody's on board with that? So I'm just doing it in place. I don't want to take up the whole new line. So this is I becoming j, and this is j becoming I. Yes?
Isn't that quantity that you have the line under, that's 9 vectors, right?
That's 9 vectors.
So, but that's 27 numbers.
Contracted with 3 vectors. So the I is in the contraction. So yes, this is 27 numbers, but this is still 9 vectors.
Oh, you put them in place, I guess.
Yeah. And combined all together, this is 3 vectors. Because there's another contraction on j. This is 3 vectors, this is 3 vectors, and of course, this is 3 vectors. So at every point, all we have is 3 vectors, 3 vectors, 3 vectors, 3 vectors, 3 vectors, but in a complicated sort of way. A set of 27, 3, and 3 vectors. And the contractions work out just right to make it 3 vectors. Now we're going to factor out zi. And look what we have in parentheses. And get used to this. In parentheses we have dvi dzk plus gamma plus, I just want to think about the order I want to write it as. Gamma give me just 1 second. Here's the order I will write it in. We haven't yet justified this being symmetric, but I'll rename it kj, vj, zi. We've experienced the fact that it's symmetric in kj, but haven't yet proven it. It's very simple, but nevertheless. Okay. Here's what we have in parentheses. So tell me something about this. Tell me something about this object. Tell me something nice about this object.
It's a tensor.
It's a tensor. You saw this on a couple of exercises you did last week. Was exercise 90 one of them? This is a tensor with vector elements. It's a set of 3 vectors that as a set form a tensor. And these are the components of a tensor with respect to the covariant basis. So this combination is a tensor. This combination is a tensor. That's a very important realization. Super important realization. This is a tensor. So wouldn't it make sense, even though This is not a tensor, this term is not a tensor, and this term is not a tensor, but this sort of combination is a tensor. And if here the interplay of indices seems to be a little bit too complicated, you'll get used to it very, very quickly. So wouldn't it make sense to make this definition? And we'll now use this symbol because it'll be a tensor. So of any tensor Ti, you define it as the partial derivative dzk, and then plus, and now watch this. So plus something having to do with with the Christoffel symbol, the indices will place themselves. Do you see that I goes on top because it's on top here? K goes on the bottom because it's on the bottom here. Then there is an additional index J, which is contracted with Tj. And this is the definition of the new operator, That's called the covariant derivative. It's the partial derivative with an adjustment. And right now you're not seeing this, but this will fix all the problems in the world. This additional term will fix all the problems. The fact that you have to keep track of the covariant basis, changing from point to point, it seems like a problem. If this makes it go away. But one thing you do see is that this is a tensor. I don't even need to prove it by showing how it changes from one coordinate system to another. You'll do it on your homework because it's a fantastic exercise. But you know it's a tensor. And then there are so many things to check. Could something this complicated satisfy the product rule? I don't know. It will, and so forth. But this is the definition of the covariant derivative. Yes?
That expression that you underlined, that's before the, yes. You said that's a tensor, right?
Yes.
Is that a tensor of order 0?
No, it's a second order tensor. There are two like indices, I and k. Just like here, I and k. It went from a first order tensor, Vi was a first order tensor, to a second order tensor because you take derivatives. When you apply partial derivatives, differentiation raises the order of the tensor. So it becomes a second order tensor, so the order of the tensor grows. And the additional order is always covariant. That's why this is on the bottom. So the new order that's picked up is always covariant.
What is the difference between what we wrote?
Here and here?
No. You started off by, that.
That is a vector.
And the first term of what you underlined.
The first term?
Yeah. What is the difference between the two of them?
Well, this is the derivative of the invariant vector field.
And what is?
This is the derivative of its component, which is not the same thing as the component of the derivative. What we want is the component of this, right? So this is the rate, this is the quote-unquote invariant rate of change. Now that we have our rate of change, you can call it rate of strain. I think that's the fluid mechanics term, rate of strain. This is a triplet of vectors. It's a tensor. We would like to know its components. You might naively, just for a moment, think that, well, of course this is the component. But it's not. It would have been if the basis didn't change from point to point. But because the basis changes from point to point, there is an additional term that comes from the fact that the basis changes from point to point. So this is actually the component of this with respect to the basis. Not this. This is just half the story.
But V superscript I is a tensor.
It is a tensor.
So why
but its derivative it's not.
But you started off by saying that that's true.
That it's not true. That it's true that it's not a tensor. This is a tensor because it's the derivative of an invariant. The derivative of an invariant, too many syllables. the derivative of an invariant is a tensor. The derivative of a tensor is not a tensor, because it had the upside down smiley face.
So not all tensors are invariant, but all invariants are tensors.
Yeah. A tensor of order 0 is an invariant. We'll start our next lecture with mine just sort of summarizing that.
Oh.
And this is the component of this, not this. So here is a new operator called the covariant derivative that at the very least produces tensors out of tensors. Now we'll erase everything except that. And we'll see that something changes when it's a lower index.
I'm still confused.
I'm sorry?
That derivative, that is now operating on not an invariant.
On
That's
a tensor.
operating on a tensor.
Yes. And it's not just a partial derivative, it's partial derivative with an additional term.
So you have two non-tensors that are being added together, and that makes it a tensor. And because they're moving throughout.
That's a little hard to explain why. So I think the best explanation is what we have on the board, because this happens to be the component of a tensor with respect of a tensor with vector elements with respect to a covariant basis. Actually gave me a phone call with that very question.
Yeah.
So that's enough to prove that it's a tensor.
Okay.
Why exactly it's a tensor? How does it work out in opposite directions so things cancel? I don't have an explanation for that. It just happens to cancel.
Okay.
So one of the exercises you go through in your homework is actually writing down how this changes from one coordinate system to another, then how this changes from one coordinate system to another. The homework you sent me does it wrong, by the way, so you double check that. And once you put them together, those upside down smiley face terms will cancel each other,
Okay.
and it will be beautiful. But why, I don't have a good explanation why, except that it's the component of a tensor with respect to the covariant basis. And I have to address the question I asked before, which is what happens, I'll pose the question here, answer it here. When you decompose when you differentiate the contravariant basis, well, J, might as well put J. And then you decompose this once again with respect to the contravariant. So the same thing, the same question we asked when we were talking about the definition of the Christoffel symbol, but when the basis is contravariant. You will get three new coefficients here. Gamma, delta is taken out. What's another good letter? Phi. Phi, so it would be I upper, J lower, K lower. Right? Are these somehow related to the Christoffel symbol? The answer is yes. Here's how. So let me write down the definition of the Christoffel symbol. Gamma. One second. What am I trying to do here? Gamma K I J equals Z K dotted with D Z I D Z J. Everybody remembers this? That's the definition of the Christoffel symbol, more or less, essentially. Because that's how you recover components of a vector. And here's what I'm going to do right now. We'll apply the product rule. This is like UDV. So let me apply the product rule. The product rule becomes D of ZK dot ZI DZJ minus DZK dzj dzj dotted with ci. That's great. And first of all, you should see that it's true, because once you apply the product rule to this term, you'll get one term which will exactly cancel this, and the other term which is this. So that proves that this actually equals this. And now look what happens here. What is this dot product? Delta ki. Delta ki doesn't change from one point to another. So what is this derivative? So this is 0. So you're left with this. So you're left with this, which equals gamma kij. So let me just summarize it right down here. Nope, not here, here. So dzk dzj dotted with zi equals minus. This minus is very important. So this will persist throughout the subject. If something is covariant, it gets a plus or a minus. If something is contravariant, it gets the opposite sign. Gamma k ji or ij. Might as well write ij. Leave it out back. Which means that this object right here, right? Because now these, so if you think of this as 9 vectors, and you want its covariant coordinate, that's exactly what you would do. You would dot it with a covariant basis. That's the quote-unquote trick from what we did earlier today. You will get the coefficients, or the coefficients here are exactly minus the Christoffel symbols, and the indices place themselves. It gets I goes on top, and then j, k goes on the bottom. So this answers the question. When you deal with contravariant basis and you find its rate of change, it's once again the same Christoffel symbol except with a minus sign. And the way the indices are involved is completely different. Here, it's the upper index that's contracted with the basis, and here it's one of the lower ones that contracted with the basis. So the way they're used in the linear combination is completely different. Plus there's an additional minus sign. So if we're thinking in terms of matrices, there's some kind of crazy minus and some transpose that I couldn't even describe. But it's the same 27 entries. And you don't have to think about the matrix perspective because the indices essentially place themselves. So it's once again the Christoffel symbol, just in a different linear combination. So we're now ready to repeat the computation that led us to this, except we'll decompose the vector field with respect to the contravariant basis. Let's do that. We'll do it relatively fast because it's similar. So we start with the same vector, dv, or the same set of vectors, dzk. But now we decompose v with respect to the contravariant basis. And we use the product rule, and we get dvi dzj, the naive derivative, that's not a tensor, dvi dzk zk. That's all we would have if the basis didn't change from point to point, but it does, plus vi And now we'll go straight for the Christoffel term, because because it'll be dzi dzk. And I know what it is. I upper, k lower, so it's going to be gamma, I upper, k lower, j vj, and also with a minus sign. That's the last thing we derived, and have since erased. So I will make it yellow now with a minus sign. That's how the contravariant basis changes, but once again, Christoffel symbol, that's great. And I once again will, I'm sorry, VI, ZI. Going a little too fast, ZI. And what's going on? Never rush, even when you look at the clock. Okay, great. And I would once again want this to be ZI. I want this to be ZI, so I will rename I into J and J into I. So this becomes J, J, I. And I can now factor out Zi, and what I'll have left inside will be a tensor. So D, V, I, D, Z, J, minus gamma. I'm not even looking here, so pay attention to that. I'm not even looking here because the DZK, sorry, maybe I should have looked there. But the point I'm trying to make now is that the indices will place themselves. Lower I, lower K, because lower I, lower K, then upper J, V, J, and then Z, I. And that's the answer. So this is the component of the rate of change. And it's once again a tensor, except when we're dealing with covariant components now, there's a minus sign and the Christoffel symbol is used a little bit differently. So this inspires another definition. So you have to have different rules. It's true. It's not something that I'm going to remedy. It's true. Depending on the flavor of the index, you use a different correction. And I will then write the combined formula, which is even more sort of algorithmic. So if you apply this to a covariant tensor, it's once again the partial derivative minus the indices place themselves, lower I, lower K, upper J, then you repeat the tensor J. And that's the definition for the covariant tensor. And I will now write the combined definition, which will look like a monster. And it'll look like a monster that it's not. It's the Napoleon of the formulas. Kind of killed a lot of people, but it had a good civil code. Was it called civil code or civic code? Nobody knows? I don't know. But he invented all that equality. Well, actually, no, because that's 18-something and we're 1776. Forget I said anything. Okay, so here's the combined definition. So this rule will show you how to deal with covariant indices and contravariant indices. So let's just give a representative index with a representative tensor with one covariant index and one contravariant index. And what this long equation will imply is that every index, there will be one common partial derivative. And then every index gets its own Christoffel term. So if there is only one index, there's one additional term. If it's contravariant, it's this. If it's covariant, it's this. But if there are two indices, there will be two additional terms, one for each index. You work on every index with its own Christoffel term. And if there are three indices, then there are three Christoffel terms, one for each index. So you operate on each index. So it will be the partial derivative, dt ij dz k. Then we're dealing with this one. Because we're dealing with I first, it's plus, because it's contravariant, gamma. And then I just want to once again highlight that it's not, there's no memorization necessary. The indices sort of place themselves. So there will be I, because it's upper. K, because we're taking the derivative with respect to k, so it's always on the bottom. And then this index, I usually denote it by m, which is the one that re-involves the original tensor. So that's the term for the upper index I. You see how the Christoffel symbol steals it, and then contracts on m, and then k goes down because it's the derivative, and j just remains completely untouched in the whole process. Okay. Minus gamma, once again, all indices will place themselves. We're now operating on j. So there's a lower k because the derivative with respect to m. And then it steals j. So you always just write down the first two indices because they place themselves. Then the remaining one is m, and it goes from where j was stolen. So that's how the definition reads. But implied in this definition is the algorithm which says that however many indices the input has, that's how many additional terms there will be on the right-hand side, one for each index. Each one will have its own Christoffel symbol, and that's how you use them. And that's the definition of the covariant derivative. And there is so much to test. Does it produce a tensor? Well, in these simple cases, you see that it does. What about in the more general case? There's a long proof and a short proof. Both are very valuable. Does it satisfy the product rule? It's completely not clear that it does. Right? If it's applied to product of two things. Does it commute with contractions? If you apply one covariant derivative I, k, followed by another covariant derivative m, do they commute? All of these super interesting questions. But let's first apply it to, we're going to right now apply it to three objects. It'll be kind of nice. And then time permitting, so these are two sub-definitions, we can erase them. But let's just practice applying this derivative. Let's start by applying it to the covariant basis. Yes?
Quick question. Why did you introduce a new index m?
Well, what else did I use? So in these sub-definitions, I had to introduce an additional index, that was j. But here I can't use j because j is already in the original one. Okay, what is the covariant derivative? I'll keep using k in case we have things with two indices. K of zi. I just remember this as one of the most joyous calculations of my entire life. I did it while eating sushi with my father. So why don't you guys? Sorry I'm not providing sushi. It was good sushi too. But that's the calculation that really made me connect with tensor calculus. So what you will have to do is a partial derivative, and then because it's a covariant index, you'll have to use this kind of term. So just at least apply the definition. You don't have to simplify, but at least apply the definition. Well, are you guys doing it along with me? Yeah, good. So I'll do it quietly, and then you can look up and compare. I'm using J. Since we're referring to this, I'll use M. Why don't you guys use M as well for this additional index? Who got this? Raise your hands. 9 hands. Not quite, not seeing it?
No, I did. I had a small mistake.
Oh, okay. That's. Have I ever said this on tape? Learning tensor calculus or any other subject in mathematics is making every single mistake you can possibly make. And once you've made every single mistake, that's when you've learned the subject. So until you make the mistakes, you're not really taking steps forward. You're just preparing yourself to make those mistakes. So you have to make, sometimes more than once, every single mistake there is to be made. Okay, can anybody simplify this?
The first term would just be gamma higher m.
Okay, hold on. The first term would just be gamma, higher m,
lower ik,
lower ik,
times the covariant basis.
with what index?
M.
M. Okay, does everybody agree? That's by definition of the Christoffel symbol. The Christoffel symbol appears whenever you're taking the derivative of the covariant basis with respect to the coordinate. Get 9 vectors that are re-expressed in the original basis with respect to 27 numbers. So now, does anybody notice anything?
0.
0. Isn't that nice? Well, I don't know if it's nice or not. Isn't it neat? 0. This is called the metronylic property. It kills everything having to do with the metric, the covariant derivative. So right now you just notice that it kills the covariant basis. That's a good start. How about the contravariant basis? Now, Alex, you will no longer make this mistake. Whatever mistake it is you made. dzi, dzk. Figure out this one. Just write out the definition. I'll do it along with you. Because I've been doing this for 10 years, I no longer have to reference the definition, but I don't think you ever need to reference it. This definition writes itself. So now it's a plus gamma upper I lower k m z m. There we go. What's that? Well, first, okay, I'll wait for a couple minutes for you guys to catch up. Put in all the errors that I've missed. Any more? All right. Good. Zero. Because if you express this, as we did just a moment ago, in terms of the covariant, in terms of the Christoffel symbol, we'll get exactly minus this term. So this is also 0.
Why minus?
Because when you look, maybe a page back, when you express the derivative of the contravariant basis with respect to the coordinate, it becomes minus, this equals minus gamma I k m z m. when we did the product rule, there was a minus. Boy, that minus is just everywhere. You know, that minus, when you do integration by parts, there's that minus, that pesky minus that just never goes anywhere. Well, that's that minus. So metronomic property applies to the contravariant basis as well. Yes?
I'm curious why you wrote that as a partial derivative when we read.
Yes. Oh my goodness. Oh, maybe 3 hours is too long. Thank you for noticing that. TZI. Thank you. Okay. Let's assume that the product rule holds. Let's assume that the product rule holds. I think I'll even have time to prove that the product rule holds. How about this? Do the product rule and then the metric tensor. You see, it's important. The product rule is important because I want to, so my goal right now is to evaluate this. But I want to remember that the metric tensor is the product, dot product of the covariant basis. So I'll have to use the product rule. So let's derive the product rule. Let's just do it in the case of one example of something like Ti multiplying Sj. This product. Of course, the sky's the limit for the sorts of products you can imagine. S, Tijk, SMRT, whatever. But let's just consider the simple one. And it'll just become apparent that it works always. So, by the definition, it's the partial of this. D, T, I, S, J, D, Z, K.
They're not vectors.
They're not. So all of this works for variance with scalar components and variance with vector elements. Scalar elements or vector elements. So I is lower, so it's minus gamma I, I, K, M, T, M, J untouched. And because this J is upper, it's plus gamma J, K, M, S, I untouched, T, M. Now to this I can apply the product rule.
Sj.
No, Si, Ti, Sj, Sm. Russian. Ti untouched, Sm. Thank you. Now this, I will erase it just so that I don't have to rewrite. This will now be two terms. dTi dzk, dTi dzk sj plus ti d t t s j d z k. Okay, now of course you will group this term with this term. Do you see that Sj will factor out? And in parentheses we have exactly the covariant derivative of Ti. So this equals the covariant derivative of Ti times Sj. And then we'll combine this term with this term. And here I'll factor out Ti. And what I'll have in parentheses is exactly the covariant derivative of Sm. So it'll be plus Ti, the covariant derivative of S of Sj. So I actually prefer writing it without parentheses. Just my convention is if there's the covariant derivative symbol, it applies to the letter that's next to it and not to the whole product. I usually leave a little bit more space here just to denote that. So there you go, the product rule works. Sometimes called the Leibniz law. So the product rule works. I think from the definition you wouldn't have thought that because it's such a mess. You throw in all of these extra terms, but no problem, it holds. And I have just enough time for a 1-minute calculation. Actually, 2 1-minute calculations. Here's 1-minute calculation number 1. This is 30-second calculation. Is gradient of Zi dotted with Zj, and I have to say that we just derived the product rule for a product of scalars. Why does it work for the dot product of vectors? Well, you'll just have to repeat it, it'll be the exact same thing, and everything will work. And of course, if this, by the product rule, it's grad K Zi dotted with Zj plus the same sort of thing, just I and j replace each other. Symmetric terms. And what is this equal? 0, because the covariant derivative of the basis is 0. So we're building up our differentiation table, and so far everything's 0. That's just the metronyllic property. So the covariant derivative applied to the metric tensor is 0. The exact same thing for the contravariant tensor, it's also 0. And I will show you one final thing. Think about applying the covariant derivative. So if you think about this, dv, so I'm glad I had a chance to mention this. Partial derivative of an invariant. So let me repeat the whole algorithm of the covariant derivative. It's the partial derivative plus a Christoffel term for each index. But if there are no indices, then there are no Christoffel terms. One index, one Christoffel term. Two indices, two Christoffel terms. 7 indices, 7 Christoffel terms. 0 indices, 0 Christoffel terms. So for invariance, the covariant derivative coincides with partial derivative. So I can just write this. And then remember, it will be the next equality step that's important. So this can be written as VI Zi. That's me decomposing the vector field with respect to the covariant basis. Now, look what happens here. Don't write this down because there's nothing to write down, but just get it. So I should do this by the product rule. But by the product rule, this will be 0. So whenever something dies under the derivative, we can just take it out. So when I do this by the product rule and it kills this basis, I'm just left with one term, which is this. Okay, where it just applies to this. So we're sort of back to where we want it to be, which is if you want to analyze a vector field, you just have to pay attention to its components and just operate on the components. It's just that you have to operate with the covariant derivative and not the partial derivative. So we started this part with sort of an unfortunate observation that a partial derivative of a tensor is not a tensor, to find a new operation, and now all of the great qualities of the properties of the derivative plus a few extra good ones are restored. So great operator, so we'll continue working with it in the next lecture. See you next Friday.